Good morning, everyone. Or it's morning in Finland, it's 9 o'clock here, and welcome to our webinar called The Advantage of Hyperspectral Drill Core Scanning from Exploration to Mining. I can see we have lots of listeners here. I hope you are all well, and thank you for joining us. My name is Rainer Bers, I'm from Specim. I will be doing a short intro here and talk a bit more later. With me, I have Laura Tusha from Theia-X. She will talk to you more later. A couple of house rules or guides for the webinar. We have a question and answer section later. You can, even during the webinar, you can ask your questions in the chat, which you can see on the right of the window. We will reply to those questions later after the webinar. You don't need to raise your arm or do anything else. If you have problems with this webinar, if you can't hear the voice or see the image, try to make a comment about it in the chat. If not, you just have to log out and join again. Okay. Let's start. I will start with a short intro, tell you what we are going to hear today, and then we will go on. My colleague Jussi Soukkamäki was going to host this and introduce this, but he was not able to join us today, so I will do this intro for you. We will first show you very short company introductions, not a lot because we will talk about geology and concentrate on the geological side of things, not the technical side. We will show you the value proposition, the value of hyperspectral drill core scanning versus conventional methods. We will then look at a few case studies. And after that, we will go into more technical details, show you a bit about the scanners, the hardware, the SISURock systems, not a lot. We don't want to look at the technology. After that, Laura will talk more about the Theia-X offering they have for the analysis solutions. We have divided up this in a way that Laura will talk about the analysis and the data processing, and I will be talking about the hardware and the scanners and the cameras. And last, we will have the question and answer section. If we start with looking at Specim. Specim was founded in 1995. We are a hardware company. We build cameras, we ship hardware. We don't build analysis solutions, we don't build processing solutions, except the latest ones for industrial sorting. We have today built more than 8,000 spectrographs and spectral cameras in total for clients delivered. We are a growing company, about 70 persons right now. We have offices, our head office in Oulu in Finland. Then we have offices also in Barcelona, New Jersey in the United States, and Shanghai. Plus we have a distributor network reaching all over the world. As a technical or financial detail, I could say that our compound growth rate in the industrial segment has been around 40%, so we are a fast growing company. And just a while back, we are part of the Konica Minolta group, which I think every one of you knows. If we look at the company timeline just shortly, I won't bore you with this. We have Specim was founded in 1995, and our first product was the ISA analog airborne hyperspectral camera. Few years later after that, we had the first digital airborne camera, spectrographs, and in the beginning of the new millennium, we had the first thermal camera, the ISA-OWL, and also the ISA-DUAL, which is a dual co-aligned airborne solution. A bit later, we had the SISU scanners, turnkey scanners for geology, co-registered dual cameras, the ISA-IBIS, which is a solar-induced fluorescence VNIR camera. In 2017, which was an important year, we introduced the Specim IQ, which was the first mobile handheld full hyperspectral imaging system, as well as the FX series, designed specifically for industrial machine vision. Later then we had the medium wave camera, the FX50, a new series of airborne instruments, the Specim AFX, and now we have the Specim One, the platform for sorting industry, and in 2020 we were also acquired by Konica Minolta. So a lot has happened. I will not bore you much, but this is our product range in short. On the left, you see our VNIR camera offerings from the IQ, the FX airborne cameras. We have the NIR camera offerings, several cameras there also. In the medium wave, we have one camera, the FX50, and the long wave, we actually have two different cameras, one cooled and one uncooled camera. But at this time, I would like to welcome and introduce Laura Tusha from Theia-X, and she will talk more about what they do and how it works. Welcome, Laura.
Thank you, Rainer, and good morning, everyone. I will start now with a short introduction of Theia-X, and also going then into why hyperspectral drill core scanning can become an emerging technology to be used in exploration and mining industry. So first about Theia-X. Theia-X is a spin-off project from Helmholtz Institute Freiburg for Resource Technology, which is part of HZDR. And here at the Institute, the exploration division was established 7 years ago. And during the last years, we had more and more requests for the industry to take the research as a service, as a product. And that's why we started as a spin-off, providing services to our incubator HZDR Innovation. Our main services are focused on hyperspectral imaging, but from various platforms and at various scales. So we use satellite and drone board data either individually or in combination to map extensive exploration areas. We used either tripod-based system or drones for subvertical and vertical natural outcrops or open pit, and hyperspectral drill core scanning systems. Here we work with the Specim systems that Rainer will describe into more detail later. For all these platforms, our focus is not only on data acquisition, but more on the processing side. And as the topic of this seminar says, we're going to be focusing on drill cores today. And to start, I just want to mention why we want to focus on drill cores. So exploration and mining companies drill tens of thousands of meters every year, either to discover a new resource, to characterize it, to evaluate the content. It's also later used into grade control and blasting, but I'm not going to focus too much on that. So once the cylindrical cores come out of the ground, the sample is visually characterized by the geologist, and half of it is crushed and sent for chemical assays. However, mineralogy is very important, and most mineralogical information traditionally just comes from visual observations, which are valuable, but they have their drawbacks. When dealing with large amounts of drill core, this can be very time-consuming. You will need several geologists to characterize these cores, therefore making it subjective and often inefficient. However, using drill core scanning, and here you will just see a quick animation showing the acquisition of the hyperspectral data using with the system we have here on site. You get the hyperspectral data from between half a minute with one sensor and 2.5 minutes with the full range going from visible, shortwave, midwave, and longwave infrared, including high resolution RGB that is shown here. So assuming 2.5 minutes per tray, that still makes things much faster. Then within the hour, using our data processing routines, you can get results. Depending on the case study, of course, they vary. It can be mineral maps, mineral abundances. It's all really adaptable. Then the on-site geologist can use this type of results to improve the speed and also have a more consistent logging between geologists. The advantage is also that you get a digital library for all the cores that you have in store. So it's easier to review this data than going back and reanalyzing the cores. With regards to minerals that can be identified using hyperspectral sensors, of course, depending on the spectral range that's of interest, these vary a lot. This is a very simple example of how much of variation you can see. For instance, in the visible to near infrared, minerals like pyroxenes, olivine, iron oxides, sulfates, and REs can be easily identified. However, minerals like phyllosilicates, clays, micas are rather distinct in the shortwave infrared. And then for other rock-forming minerals, and I'm going to just mention here the garnet, it can't really be identified in the other ranges, so we will use the long wave, and one of the case studies will show this. What we want to emphasize is that, through the following case studies is that the hyperspectral data and hyperspectral drill core scanning can really become a pillar in exploration and mining routines, and that it can be used from early exploration all the way through closure and remediation. In order, however, not to spend too much time on it, I'll just focus on 3 main stages. So regional exploration, sort of going a bit towards resource definition, and also a case study on optimizing the beneficiation. To start with, I'm going to go into alteration mapping and exploration targeting. So in this kind of an environment, what we want to do is find proxies or different alteration assemblages that can be used as a guideline for defining different ore types or grades or ore types. For this epithermal system we're looking at, defining ore types is very important because both copper and gold are present in various mineral phases. Especially copper, you'll have it in sulfides, you'll have it in sulfur salts, and it's really important to be able to distinguish these different types. And to define spectral proxies, we look first at a selection of cores that cover the main ore types discovered in the deposit. And following this, we build a spectral library specifically for this ore type. Now, for major alteration minerals like clays, micas, carbonates, and sulfates, it is relatively easy to get a spectral library either using the very good existing ones like USGS or CSIRO, or developing one from the samples. When it comes to trace minerals, minerals that are key and they act as proxies for specific ore types, but they're not present in high amounts in the samples, or they're not common in many spectral libraries, then it's important to create for these specific mineral groups a new library. And this is the case here. So besides the many types of micas and clays, and also alunite and gypsum, so the sulfates, we also want to look at other aluminium phosphate sulfates like crandallite, svanbergite, woodhousite, but also etzunite. And for this, we developed a spectral library using samples from the museum here at the university in Freiburg. And then we use this information to start mapping the abundance and different properties of each mineral. Now, I'm not going to go through all those minerals. I'll show just my kind of first stage as an example. We can see there's a strong variation in the abundance and distribution in the different domains that we see here of the mica. In addition to this, the composition of the mica varies from paragonitic muscovite to phengite in the cores, and not only within one tray, but you also see variations inside the tray. So these variations can also serve as proxy towards going to a different mineralization style. Other parameters like crystallinity of the mica can always be calculated, and these are also included then in the definition of the domains. Now for the APS minerals, you've seen, probably you've noticed in the spectra that they are relatively similar to alunite, and especially what's really important is that they occur in mixtures. So then finding a way to distinguish them is really important. And for the most common APS mineral here, svanbergite, that occurs together with crandallite, we can see a shift in the absorption feature compared to alunite, and then we are able to distinguish them. Now, putting all these pieces together, the abundance of each mineral, all micas, clays, chloride, and so on, and their composition, also same for the APS minerals, you can then define mineral domains or mineral association maps. And we will see that while kaolinite tends to be strongly distributed through many of the domains, its association changes strongly. In this first domain that you can identify here, so in this tray, it will be associated with a lot with alunite and also APS minerals that are found as fine disseminations together with alunite. In other cases, it's simply only with alunite, or it starts occurring with only gypsum or with dikite. So these mineral associations can then really become representative of the different modes of occurrence of mineralization. It's always important at the end, after you've created this map, to validate each domain. And for that, we evaluate the spectra inside each of the domains to make sure that the mapping was successful and it was representative. This is it for regional exploration. Is just a short example, and I would now move towards resource estimation. And this is a project we worked on in collaboration with Arctic Mineral Resources, and it was about finding a way to quantify the garnet distribution here, almandine. Almandine is becoming more and more researched because of its good performance in abrasive blasting. However, due to its geochemical similarity to the surrounding gangue minerals, such as amphiboles and chlorides, it becomes very difficult to evaluate its abundance just simply on geochemical assays. And then if you want to use automated mineralogy, such as SEM-MLA or ChemScan, it also becomes really expensive. The throughput is limited, because you either look at thin sections or end up looking at grain mounts, but over much more extensive intervals. And therefore, we wanted to develop a mapping approach to estimate the abundance from drill core data. And as I mentioned earlier, garnet is spectrally diagnostic in the long-wave infrared, and that's what we used here. However, we also used high-resolution RGB data in order to enhance the hyperspectral data to make sure that area where the garnet is altered to amphibole that may be very thin and sort of like veinlets or usually under the resolution of the hyperspectral data can also be well characterized. I'm going to show here an example of one tray. We will see, as you would expect in an eclogite, alternations between the almandite-rich areas and the omphacite-rich areas. Besides this, there will be some quartz veins, carbonate veins, and also areas that are richer in amphibole. However, they cannot very well be mapped, as I mentioned, just using the long-wave infrared data due to the spatial resolution. And so also just using the long-wave data, we will be able to map the mineral abundance, so the abundance of each of these minerals. However, for amphibole, again, you will see this sort of blurry appearance. You can't really narrow down exactly how well it is concentrated. The advantage of using hyperspectral drill core scanning, and I'm going to jump then back later to the resolution enhancement, is that you can also get the model mineralogy straight for every meter. Of course, you can do that at centimeter scale. It's just a matter of choice, like what would be the resolution that's interesting for resource modeling. And all of this can appear then into logs. Here you'll see more minerals because we looked at different ore types, and this kind of compile the whole thing. Now, when looking at resolution enhancement, the amphibole starts being much easier to identify over the very, very fine structures where it occurs. And maybe I just move here to actually show a comparison that once we look at the enhanced resolution, we are able to actually really see the enrichment of amphiboles being present more often than originally expected. And this can then be used to correct for the garnet versus amphibole abundance in the entire logs, and therefore in the whole resource definition process. All right. I will now move ahead to grade estimation and sorting simulation, and we're going into a completely new geological system. So we're looking at Greisen type ore and specifically for lithium. We're looking at lithium due to the increased demand for battery material supplies. It's something that you always hear, especially in Europe, that we want to find domestic resources. And we worked here together with GeoMed. The objective was to do the high resolution mapping of Zinnwaldite abundance, not only as you get it when doing the assays over meter intervals, but really being able to map the Greisen layers that sometimes go from a few centimeter scales to meters. And for this, we used visible near-infrared and shortwave infrared hyperspectral imaging. This is a simple example of the mineral abundance maps that we get for the major minerals that are diagnostic in the visible shortwave near-infrared and shortwave infrared range. And in this case study, this will be Zinnwaldite. It will be clay, mostly occurring as kaolinite, very locally halloysite, muscovite, and topaz. And the same as before, we can look at this throughout the borehole and also look at different associations, different ore types. So Zinnwaldite in most cases tends to be directly associated with topaz. There are some areas at depth where this is not the case. And frequently it starts occurring together with the clay, which is something that may cause problems in the beneficiation process. It's something to keep in mind. This would also be the case for topaz. However, it's relatively easy to separate later on. And here we worked also in partnership with Erzlabor, another spin-off project providing automated mineralogy data here at HIF. And they provided some MLA analysis on some of the samples. And we could use then this some MLA analysis to develop a model to predict the grade from the different spectral parameters of the Zinnwaldite. And to do this, we've estimated then the grade at 1 meter scale and at centimeter scale. And you can see good correspondence between the assays, which are per meter or per 2 meter, depending on the general grade, of course, and the 1 meter estimates from the hyperspectral data. However, when we look at the estimates over 5 centimeters, we start seeing more variations, just showing how complex the system actually is and how many fine alternations you will see between the Greisen and the albite granite. And then, as a next step, what we can do is use these 5 centimeter estimates to simulate the potential, the sorting potential using shortwave infrared sensors for this deposit. And we're going to look at the same borehole example. And here we plotted both actually the 1 meter and the 5 centimeter scale estimates. And we can see that there is a possibility to strongly upgrade the ore. So you will get a 90% Zinnwaldite recovery at only 60% gangue recovery. What this actually means in practice is that you will recover so much of your Zinnwaldite and discard 40% of the barren rock, 40% that will not go to crushing, well, to fine crushing at least, and to grinding, reducing a lot the energy that is being used in the plant. And to summarize for now, I just want to say that I do believe, and I hope that these case studies have proved it, that hyperspectral imaging applied to drill cores can really improve the logging routines and can have a strong role in every single step going from exploration to mining routines. I think right from my side, this is it for now. I will let Rainer continue presenting the cameras and the scanning systems, and then we can move forward to also presenting how Theia-X provides their services and what kind of service packages we have. So, to you, Rainer.
Thank you, Laura. That was very interesting. I'm always amazed of what you can do with this technology. Even though I have been in this company for more than 20 years, it still surprises me. But we have now looked briefly at the what and the why parts of what we do. We will now take a glimpse at the how. We will look at a bit of the technology and the analysis behind it. I will not talk very long about the cameras and the hardware. It's not interesting from a geological perspective. It's enough that it works. So, briefly, I will look at Specim cameras and scanners for geology and mineralogy. Excuse me. We will look just shortly at how this technology works. We will have a very brief glimpse at our camera and scanner alternatives, and then the drill core scanner SISURock layout and the camera options we have there, and the benefits of SISURock compared to other scanners on the market. And then a word about the workflow and some practical considerations. Probably most of you know that in hyperspectral imaging and spectrometry, we are measuring usually reflected, visible, and infrared light. Molecular and electronic vibrations in the target material receiving the light, incoming light, will absorb specific characteristic wavelengths of the reflected light, which you can see in the image here on the left, right. There are two sample mineral spectra there, and we can see that the dips in the spectra are very different. It depends on their chemical composition and the molecular vibrations there. This allows us to identify minerals using spectrometry. Specim cameras are all imaging systems, meaning that we build an image of the target, say a drill core box. Excuse me, my throat is a bit dry. We collect and record a spectrum for each individual image pixel, like in the image we see on the right there. You can imagine this is the red part here is a drill core box, and for each pixel we get the full spectrum. Down below we have an example drill core box of long wave thermal infrared measurements. Specim builds hyperspectral imaging cameras for all the major wavelengths. Visible near infrared, shortwave infrared. We have a combined common 4 optics VNIR shortwave infrared camera. We have quite a new medium wave infrared camera, and we have an imaging long wave infrared or thermal infrared, as it's also called. We also build scanners around the cameras for many sample sizes and applications. In the images on the right, you can see a small lab scanner, a tabletop device. There is a bigger lab scanner under it in the middle. These are single camera scanners. Down on the right is what we call an art scanner. You know that scanning paintings and looking what's behind the paint layers of old paintings is now very interesting. And on the bottom we have the SISURock, the drill core scanner, which is a multi-camera instrument designed for drill core scanning. If we look at the SISURock drill core scanner a bit closely, it's a commercial turnkey system which allows one or several cameras to be combined into one scanner, from VNIR to shortwave, medium wave, long wave infrared, plus the option to have an RGB high resolution photo or image of the drill core. The SISURock is the only commercially available scanner with an imaging long wave and medium wave cameras available as options. All other cameras or measurements in these ranges are profiling, meaning that they create a profile along the core, not an image. The SISURock also has a very high sample throughput. As Laura said, measurement with a single camera takes about 1 minute, and if you have several cameras in the frame, about 2.5 minutes per box from loading to loading. That means that in a single 8-hour shift, you can scan upwards of 200 drill core boxes, meaning more than 1,000 meters of drill core in a single shift, depending on how much core you have in a single box. That is a lot of core. It's a hungry system. The current options for the cameras we have now for the SISURock is, of course, the high-res RGB. We have a VNIR camera options, if that range is of interest for rare earth elements, for example. Then, of course, the shortwave camera, which is kind of the baseline for geological, mineralogical measurements. Many of our clients use the combined VNIR SISURock camera, the Phoenix, covering both these wavelength ranges. The medium wave has been very interesting because it's a new wavelength range for this application. It has not been around that long, so we don't really know that much about medium wave and its applicability to geology and mineralogy yet, but we have seen great interest in it. Then we have the cooled long wave camera, which we call the OWL, which is a great camera for geological applications because it's able to identify many of the rock forming minerals you can't see in the shortwave infrared. Currently, we are exploring and evaluating and probably going to integrate a 3D laser scanner for core box topography, which you then can use for geotechnical applications like calculating RQD. This will also be an imaging system. You will get a topography image of the entire core box, so you can use that data also for masking of the core box or something else. What makes the SISURock unique in the market? What's the value of it? The SISURock is not a profiling instrument, it's an imaging instrument. We will capture the sample texture too. And that gives a lot of added value in many applications, geometallurgy, for example. We have several cameras mounted in a frame, and in a single scan, we will capture data from all cameras. We have no need to reposition or the core or the layout of the core in the box. All cameras will see the same side of the core when it's in the box, and you don't need to remove the core from the box. Specim is the only commercial company providing imaging long wave and medium wave cameras, which can be used in scanners. And as Laura said and I said, the SISURock is fast. A shorter scanning time means lower cost to the end user and client. At this point, I would like to show you a short video describing how the measurements of SISURock, what the workflow looks like. It takes about 3 minutes. Let's see.
First step in measuring drill cores is to move the core from the archive to the workstation. The core surface has to be reasonably clean and dry during scanning. But both core preparation and scanning can be done while the core is sitting in its original tray, saving time and effort. Metadata information like tray start and end depths and box numbers are recorded if not already available. These, along with other metadata, are later stored on disk together with the scan data. Before the scanning project starts, the workstation is adjusted for the specific core tray height, width and length, and other tray and project-specific parameters like capture folder on disk and dataset naming. The scanning is fast, so feeding the machine with samples becomes crucial for achieving a high throughput. A roller table or conveyor system with loading-unloading buffers helps. Project, borehole, and tray-specific metadata like borehole and tray numbers and core depths are entered by the operator and stored on disk, along with the scanned data for each core tray. Automation helps eliminate any data entry errors. A white and a dark reference scan are stored together with each individual tray scan. These are used to normalize data to reflectance and to compensate for any changes in system response with time and to ensure that data quality is high. Scanning a core tray typically takes only 1 to 2 minutes from start to finish. The data is collected and stored on disk in a single scan, capturing a full spatial image of hyperspectral data with all of the cameras simultaneously. The data is stored in a structured folder, each scan in its own folder with machine-readable metadata to enable easy batch processing for analysis. After scanning, a quality analysis and quality control routine lets the operator visually verify that the data is complete and everything is included. If needed, the data is easy to rescan at this point when the tray is still loaded in the workstation. You can reach scan rates of more than 200 core boxes shift easily. A lot depends on how effectively the core trays can be loaded into the scanner.
Okay, thank you. Let's go back to the slides. Last but not least, measuring the core is only the first step. We need to transform this raw data to information and then to geological actionable information. How do we do that? We need a verified scalable analysis and visualization solution available, and it needs to be used to extract information from the raw data. And Laura will talk more about this part now, about the processing and the analysis. Thank you.
Okay, thank you, Rainer. I'll just get back to my screen sharing now. And back to the same, sort of the same slide as before. So I'm going to go now into the different packages that we have for the core services that we provide. And we divide them into 4 main packages with several add-ons. The basic one, Core S, covers data acquisition when that is required, when the customer doesn't already have the system on site. Going into spectral analysis, evaluation, and definition of mineralogical and of spectral domains and implementing these. Now, the way these are provided depends from client to client. It's always based on the composition of the ore that we're analyzing, and we usually just adapt the methods to each ore type. Going to the next type of service, the Core Plus, this one relies more on supervised machine learning techniques. Based on the domain implementation in the previous stage, we select representative samples from each domain, And we upscale this information that we obtain from the samples, also allowing samples for result evaluation and error estimation. Now, the sample selection will depend on the type of measurement that you want to do. Sometimes no sample is needed because handheld measurements would be taken, and you would upscale this, say, handheld XRF data to the entire drill core scale. Or sometimes we just fuse the full meter geochemical data to the hyperspectral data to provide more high-resolution information into the geochemistry. One of the very common tools that we use is using automated mineralogy data, can be SEM-MLA, ChemScan, it really doesn't matter. Co-register this data to the hyperspectral images and build either a classifier if we're just interested in a mineral map, or if we're interested in ore versus waste classification, or a regression to create mineral abundance maps. So this way, you actually get model mineralogy per meter, per centimeter, depending at the scale that you're looking at. Additional to the two work packages that I mentioned first, there's also the FAST package, which means that with this, we use a developed model to provide near real-time data processing, so it's available within minutes for the site geologists to continue the evaluation of the cores. And the results that come from the previous packages can also be processed in such a way that the domains, here you will just see a continuous clay abundance estimation over the boreholes, but also get labeled domains that make sense into for 3D modeling. So not having these fine variations that you obtain because you look at a very high resolution in the hyperspectral data, which is very useful for many things, but defining domains by analyzing what comes in the interval. In addition to this, I mentioned that we also have some add-ons, and one of these is the resolution enhancement. So that is what I also presented in the Garnet case study. We used the high-resolution RGB to enhance the original hyperspectral resolution to a much better one. And here you could see, again, the example going from mineral maps at original resolution, that's 1.5 millimeters per pixel, to a higher resolution. As a second tool, we also do structural feature extraction. This can be very useful for vein type deposits, quantifying the vein density or defining the vein composition or vein alteration halo composition. And the third, that was recently just developed at HIF. I think maybe I did not clarify very well the collaboration we have. So we're always in close contact with the research institute here, taking all the new technologies and data processing routines that they develop to the market. And this is what they've recently worked on. You will see that being able to visualize straight on your cores using a tablet, the different data sets that you can produce on the cores. So here's just an example looking at the MNF and the Cookite abundance, which is one of the target minerals here. And then being able to really pinpoint areas of interest, you can take further measurements such as handheld XRF, LIBS, or whatever other tool that you have at hand and you want to use. Another piece of news from our side is that we've just finalized our processing platform, meaning that now the customer is able to upload their data straight to our service, straight to the platform. And we right now provide the data processing and visualization tools right after. This is the first step out of a bigger plan in which the customer can also be part of the data processing routine and work together with us on the platform. This is just a short example on the visualization tools. So you can connect onto it straight from our website, of course, having a username, a functional username for that. And you can check first of all, the status of the data processing. Here, for this example, it's just one short borehole, but it will come up in a second. There it is. Showing the status. So we have the mineral library, so the spectral mineralogy that you can visualize either like this as stacked spectra, as individual spectra. There are several options depending on what is useful for the customer. This is a useful tool, especially when we have customers that are interested in understanding the spectral mineralogy and wanting to evaluate what was done. Then you can look into the abundance of different minerals. Here it's just an example of abundance logs, here using the Core Plus approach, so using the upscaling based on SMMLA data. These, of course, can be visualized as mineral maps as well. But we just skip that part, and this is more of a summary approach. So for this case study, we've defined also alteration domains and mineral domains for the deposit. And then you can see down the borehole the domain labels and mineral abundances, as well as the vein density estimation, which was done based on the mineral abundance estimation for the sulfide. So this is it from my side right now. I want to thank you all for the attention, and I'm open for questions.
Thank you, Laura. Like with the technology, I'm also always impressed by these analysis methods. I'm not a geologist myself, so it's a bit like magic to me. Now we are open for question and answer. So please type your questions in the chat window, and we will answer them with Laura. I don't see any questions yet, but I have a question. Would be interested. A lot of geologists and mine sites use 3D modeling packages to resource estimation. Do you have a connection between your software or your results into those, or how does it work?
So for each project, normally we export these mineral abundance logs or domain logs or whatever the product ends up being in such a format that it can be imported. It's something that's relatively easy, but also very useful to be able to practically use the data at the end the way you need to, because it's not just about looking at pretty pictures.
Yeah, that's true. Now we have a first question. Mark Fimeri asks, what is the typical turnaround time to provide results? I think that's for you.
Yeah. Well, once a spectral model or data processing approach is designed for a customer, and we tend to do that a lot in orientation studies where we define the data processing routine that we upscale after, within the day you can get the results.
So in one day?
Yes. Sometimes it's within hours, but I want to be conservative here. And
okay. So once the model is built.
Exactly.
Okay.
And also for the quantitative approach where you already have the model based on the training data, it is very easy to implement. It just requires these validation steps that we need to do before providing the data to the customer. I think that's always important.
Okay. We have another question from Thomas. Great stuff. How sensitive is the quantitative analysis for core surface curvature or tilt?
Yeah. For the shortwave infrared or visible near infrared, we've seen that the effect is very low. However, there's normalization that's required when using the long wave infrared, because you obviously don't have consistent heating of the sample when you have the rounded surface. And there are higher errors for that specific case. It's still feasible, and one approach that we do if we want to quantify really the mineral abundances is to use a thinner strip over the core. So for the mineral maps, we use the full thing, but to ensure that the quantification is within good ranges, we narrow that down. So we create a mask over it, let's say.
Okay. Just as a thought, because usually you look at the absorption features, the positions and depth in the spectra. It would seem that even if the signal level is lower at the edge of round core in the long wave, you would still see the same absorptions, and with some kind of hull correction or something, you could actually use that. I don't know. What do you think?
Well, I think it really depends, because you sometimes go in the approach in which you map the depth location of absorption features, and for that, yes, you use Hall correction. However, sometimes, especially in the long wave where you have the strong mixtures, you already have several effects related to the mixtures on where you have the spectral features. And then changing so much the, sorry, I was just reading the next question I shouldn't have. Changing so much the heating intensity, that plays a very big role. For the shortwave infrared, however, we can tackle that. But also there's an important Hall effect that also plays a role in the quantification, and that's something that should not be completely discarded. Yeah.
Okay, thank you. I understand. Then we have a question. Does the SISURock camera work stable during long time operations over hours? Maybe I will address that. The answer is yes. It's temperature stabilized, even the optics of it, and it is really stable once it comes up to operating temperature, which takes like 15 minutes, 30 minutes until it's like maximum stable. And also, we measure the white reference and the dark reference. The dark reference is the background signal level for each individual scan, so we can correct the camera system response change for each scan also. Hope this answers the question. Okay. And then we have another question. Is there some experience in using the Specim IQ, the handheld VNIR, out in the field? Yes and no. I'm not an expert in the Specim IQ, but I know it has been widely used in the field. I'm not sure it's been used that much in geological applications because it's VNIR and the applications are somewhat limited for that. We could talk more about this. We have other people at Specim who know more about the IQ and the applications than I do, personally. Then we have Chris asking, do you have or use a polarizing scan or integrated polarized and standard scan? No, we have not used polarized methods for these reflective measurements. Specim's cameras are practically polarization independent, so we get all polarizations, and we haven't used polarization. I think polarization is usually used only for thin sections. Am I correct, Laura? Or
it would be useful at some extent, and that is sometimes implemented in microscope systems, but I have not used it on a drill core scanner.
Yeah, our measurements in the drill core scanner are reflectance measurements of a diffuse type. So I wonder whether the polarization has an effect at all there. I don't know the answer to that. Then we have Lucas asking whether we have any geotechnical and or geophysical properties applications.
I did not go into those case studies today. I tried to keep it short to 3 of them. We've worked a lot on, especially in outcrop scenarios, at quantifying or the abundance of minerals that can create problems with slope stability, such as different sulfates that hydrate or clays. And the same thing can be done in cores, also to develop a model for it, but I did not go into detail on that. With regards to the hardness of the rock, like physical properties, I think this is sort of also what you had in mind. Estimating that from the model mineralogy can be done. It's just we always have to be aware that we lose some of the textual information unless we do the resolution enhancement to also see the grain sizes of the minerals in question that play a big role on the physical properties. But this as well is achievable.
Yeah, and we are implementing or investigating the use of the 3D laser scanner for the drill core on the SISURock, which will give you fracture densities and things like that. So yes, we have. Please go on.
just wanted to say that this can also be done through image analysis, but bringing in the laser will bring a higher level of accuracy.
Yeah, true. Okay. Laura, if I may be curious, I don't know whether this is your company inside information, but how do you mask the core from the box? It's always a problem and very...
Yeah, that's one of the questions we receive very often, this and how we automatically co-register different data sets.
Yeah.
But yeah, that is something I cannot answer, I'm sorry.
Okay. I saw it can be done, so...
Yeah, I was avoiding presenting it in order to avoid that question.
Okay. So I don't think we have any other questions now here. We will wait a minute if there is something else still. Okay. You can see Thomas has a question. I think that is for you. How the spectral derived model abundance is compared to those of the XRD?
All right. We usually validate these with remaining SEM-MLA or XRD analysis. And we see that for the spectrally diagnostic minerals, they are very good. I think I would say that they are reasonably similar to the XRD. What becomes more problematic, especially when only using a small selection of senses, so not the full range, we will see much higher errors coming on feldspaths, and sulfides we usually have to treat as a group in this case, sulfides, sulfosols, and so on. But the sphere diagnostic are indeed comparable to XRD.
Okay, thank you. So let's wait a few seconds more. We are almost at the end. Sorry, end of our 1 hour webinar here. We had some very good questions here, I think. Great interest. I like it that we have lots of geological questions. It means that geologists are listening to this, which is good. Okay, Lucas has a question about kimberlites.
All right, so I personally have not worked with that. I would have to ask my colleagues, but maybe feel free to drop an email about that, and then I can try to answer you.
Yes, that's the approach we take when we can't answer here. Please, we'll tell you more, but we'll tell you later.
Sorry.
We don't have the information always here, and might be a lot of it. Okay, Chris is asking whether the scanner range could be extended into UV.
I have that question too.
Yeah, you have that too. Technically, yes. In practice, Specim does not have UV illumination or cameras for the UV currently. UV also poses some problems in terms of work safety and things like that. So technically, yes, but there is no easy way to do it right now. We don't have the design for that. And I don't think we are planning on doing that. There is not much demand for UV scans. Okay, it is 10 o'clock and I think we will follow up. Lucas is asking, is this recorded? What does our administrator say about that? I don't know.
Yes, as I just typed in as a message, this will be recorded automatically and you will receive the link to the recording later today.
Yeah. Okay. And everybody heard that and not just Laura and me. Thank you. Thank you very much. It was a pleasure talking to you. Hope to see you soon again later. Thank you for your interest.
Yeah, thank you.
Yeah. Bye-bye.